simple, but it's a little bit more complicated than it looks. Your intuition sometimes fails you. So this is this example, and suppose you alternate between forward and reverse searches. So you start by scanning S, and you discover path of length 2 to A and the path of length 5 to X. And then you scan T, and you discover that the distance from X to T is 5, and the distance from B to T is 2. So next you scan A, it's the smallest one in the forward search, and you discover, oh, by the way, in this, here you also discover this path of length 10 from S to T. Now you label B having distance label 7 in the forward search, and you discover this path of length 9. So next you scan B, and you basically didn't discover anything interesting. And next you scan X in forward direction. Again, you don't discover anything new. And then you about to scan X in the reverse direction. In this case, you stop, but notice that X is not on the shortest path from S to T. You have discovered shortest path, it's this one, but X is not on it. And so intuitively, X should be on the shortest path, but it isn't. So this is an example graph. It's for historical reason. It's sort of north-west of US and some parts of Canada. So basically, the more intersections there are per pixel, the darker the pixel is. So these dark areas correspond to cities. So this is Portland. This is Seattle area. This is Vancouver. And so this is, if you do shortest path Dijkstra's algorithm from here to here, this green area is what was searched by Dijkstra's algorithm. And by the way, here in this example, lengths represent arc transit time, so it's driving time. So it's not a nice circle because highways are sort of faster. And bidirectional Dijkstra search is about half as much, but again, it's still lots of vertices. And so how do you reduce it? So one idea is that of A-star search. And A-star search is an old classical artificial intelligence technique. It came from searches on very large graphs. Think about games, like a game of chess. We have an implicit graph where legal positions are vertices, and there's an arc from vertex V to vertex W if there's a legal move which brings you from one position to the other. Okay, it's a huge graph, and you want to find a path from, the starting position to some winning position, for example. And so you want sort of faster algorithm than just doing Dijkstra and looking at just too many vertices. And so the idea is, suppose you also have pi sub t, which is a domain-specific estimate on the distance to t. So the idea is A-star search is also known as directed search. You want to direct your search towards the destination. And so you have estimates on distance to the destination, and the sort of logical thing to do is, instead of picking the vertex with the smallest distance label, is to pick the vertex with the smallest estimate on the distance to the destination. So you have d sub s of v, which is your current length of your current path you found from S to V, and then you have this estimate on the remaining distance. So you pick the vertex with the smallest value of k, where k is this sum. In general, optimality is not guaranteed. So this is not guaranteed to find the shortest path, but there are interesting cases where optimality is guaranteed, and to do this I need to define reduced costs and linear programming sort of terms, but you can just define them by this formula. So basically what happens is, for each vertex you subtract some number for all incoming arcs, and you add the same number to all outgoing arcs. So if a path goes through a vertex, its length is not affected. And if a path, say, terminates in a vertex, all such paths are affected by the same amount. And same if the path starts in a vertex. So what it means is that if you have two paths between S and T, their relative lengths, the difference in their lengths is not affected, right? And so it means you have an equivalent problem. So if you have an equivalent problem, but of course a ball in this transformed space, this where you replace original lengths by reduced cost, a ball looks differently. And so the hope is that you will search a smaller volume ball if you do it in the right transformed space. Okay, so that's the idea. And then we define this potential function pi to be feasible if all reduced costs are non-negative. Okay? And then it turns out that a star search with respect to this particular feasible pi is equivalent to Dijkstra's algorithm on the graph with cost replaced by reduced cost. And since Dijkstra's algorithm is correct, if all arc lengths are non-negative, if pi is feasible, it means that you get an exact algorithm. A star search is exact. Okay, and so any questions so far?
Why is it called feasible?
It's a linear programming term. It's sort of dual feasible and linear programming. It comes from linear programming.
Okay.
Okay, so the only question remaining is how do you find these lower bounds? So a classical sort of thing to do is to use, at least for graphs embedded in, say, in a plane, like maps more or less are, is to use Euclidean distances. Okay, and this is not a very good bound, especially if you are talking about the driving time. Because if you do it in driving time, you have to also account for the fact that speeds are different in different roads, and you have to take the worst case speed difference, which is something like a factor of 4 at least. So you are at least a factor of 4 off in your lower bound, and this is bad. So one contribution of our work was we suggested to use triangle inequality. So suppose you have a vertex A, and we call it a landmark vertex, and you pre-compute the distances from A to all other vertices. Then you can use this to get a lower bound on the lengths of VW by looking at this triangle and writing an obvious sort of triangle inequality, that distance from V to W is greater or equal to distance from A to W minus distance from A to V. Okay? And notice that people often get confused here. The graph doesn't have to, arcs in the graph don't have to obey the triangle inequality. But distances in the graph always obey triangle inequality just because they're distances. Okay? And so you can do the same if you pre-compute distances to some other landmark B. Okay, so this way you can get lower bounds. And also notice that maximum, it's easy to prove that maximum of feasible lower bounds is also feasible. So what this allows you to do is you select some number of landmarks, basically as many as you can afford to store distances to and from. Then during pre-processing, you pre-compute distances for every landmark. You pre-compute distances from it to all vertices and from all vertices to it, and you store that. And this gives you a fast way of computing lower bounds. And so intuitively it works well, because if you have a sort of a destination and landmark sort of more or less in the same direction behind it, then if you think about road networks, it's sort of you go to some major highway and you take this highway, and then at some point you get to a local exit and this path split, but for a long interval this will be the same path, and it's easy to see that in this case the reduced costs of arcs with respect to lower bounds given by this landmark will be 0 for this common interval of the path. Okay, and your search will very quickly go to here. Okay, now let's talk about bidirectional algorithm. So you can do sort of a symmetric thing in the other direction. So you have forward reduced costs and you have backward reduced costs. And I claim that you cannot just run the bidirectional search using these length functions. Does anybody see what the problem is?
They won't meet.
Sorry?
They won't meet.
No, they eventually will meet.
Yeah, but probably too late because one will go to one highway and one.
No, we will
No.
have estimates to different, one for 2000 and the second to budget, and we will have a reweighing on the graph actually, but we will have two different reweighings.
Right, exactly. You have two different reduced costs. And so you're doing a forward search with respect to one reduced cost and backward search and the other reduced cost. So it's not true that when the searches meet, you have the shortest paths, because they're different. And in fact, we actually we know that they don't do this because we implemented it and it didn't pass self-check, and then we realized that this is wrong. And of course, it's known that it's wrong. And there are several ways of dealing with that. And the easiest one is to use the idea of Aikida et al. And so what you do is essentially average the forward and the backwards. In forward direction and backward direction, you just define this potential to be minus that potential. So in general, if you have these two potential estimates, and if they add to zero or to a constant in every vertex, you get the same reduced costs. So this has some consequences. This is, you sort of are taking lower bounds on distances to t and from S, and you average them. And this doesn't give you necessarily such a good lower bound on distance to t, which is what you are interested in, but it gives you correctness, and it still sort of is not a bad bound. And so alt algorithms are the algorithms which use a star search with landmarks. So you compute your lower bounds using landmarks and triangular inequality. So alt stands for A star, landmarks, and triangular inequality. Okay, so now how do you select landmarks? Well, you can do it at random, just pick some random vertices. It turns out you can do better, and if you think about it for 10 minutes, you'll probably come up with 2 or 3 heuristics, and maybe they'll be better in ours, maybe not, but I don't want to go into details. These are sort of things you just play with it, you get some intuition, and then you see how it works. But one sort of additional idea is you can use local search to improve quality of your landmarks. You can sort of come up with a superset of candidate landmarks and then use local search to get better ones. And there's some preprocessing query trade-off, because if you spend more time selecting landmarks, you may be able to select better landmarks, and then your query time will be faster. And query is very simple, right? You just do this transformation on the fly, kind of. But there is also another sort of improvement, because if sort of I'm going from Moscow to Yekaterinburg, then a landmark in Vladivostok may be useful, but a landmark in Murmansk will be useless. And this is sort of the idea of active landmarks. You sort of see which landmarks give you better lower bounds, and you use only those. And you can use this idea dynamically, because as search progresses, sort of different landmarks give you better bounds maybe. So you sort of, as the search goes on, you still check if other landmarks can become useful as search goes. And this is very effective. Usually about only 3 landmarks are active, no matter how many landmarks we have. And so this allows you to have many, many landmarks and pay only in storage costs. You pay essentially nothing in a query cost. Okay, so this is the same example as before, and these diamonds are landmarks, and yellow diamonds are landmarks which were actually active during the search. And as you can see, and so again, as before, green is forward search, vertices visited by the forward search, and blue are vertices visited by the reverse search. And you see that the search space shrank a lot, and you still found the same optimal path. And sort of, I'll give some experimental results. Some of that is outdated, things it became a little bit faster, but it should give you an idea. So this is on the same vertex with 1.6 million vertices, and here is pre-processing time in minutes. So Dijkstra's algorithm needs no pre-processing, and alt algorithm was taking 4 minutes, and graph occupied 28 megabytes, and graph plus landmark distances in this case, where we use 16 landmarks, occupies 132 megabytes. So it's you increased your storage space, but the running time in milliseconds went down by more than an order of magnitude, and also in terms of number of vertices scanned on the average and maximum over 10,000 runs also decreased a lot. So you got a big saving. So sort of to repeat myself, A-star search was used for maps for a long time, but with Euclidean distances. And there it actually doesn't help much. And to make it help, people sort of do heuristics, like they multiply this lower bound by a factor of 2 or 3 or something, and then you sort of get faster, but you lose optimality. But that's okay, because optimality was already lost before. So, but using landmarks, you keep optimality, and you get actually better lower bounds. Okay, are there any questions? Because I'm going to start on talking about reach. So now it's a good time to ask questions about A-star.
It's clear.
Okay, so reach is also, the definition of reach is a little funny, so let me tell you the intuition first. So this is a map of San Francisco Bay Area, and so this is San Francisco, this is Oakland, and this is Treasure Island, and there is an exit from, so this is Bay Bridge, and there's an exit on the island. And as a human, if you're looking for sort of a way to go from somewhere in San Francisco to, say, somewhere in Oakland, you don't need to get off the highway and search intersections here, right? So it would be nice, but Dijkstra's algorithm, of course, will. So it would be nice if it were smart enough to not to do this. And the idea of reach allows you to do this. It allows you to, it's actually a very pretty idea. And it allows you to prune the search. Okay, and intuitively, if you think about it, if you think about some intersection on the island, if this intersection is on some shortest path, it means that the shortest path either starts on the island or ends on the island. Right? Because there's no shortest path which sort of goes like this, and you take the exit, go here, take the entrance again, and go back. Right? So this is the idea. So for any shortest path which involves some intersection on the island, this path has either a short suffix or a short prefix. Right? Okay, and that's the intuition. So now you should understand the definition of reach. So if you have a path and the vertex on the path, then reach of vertex V with respect to this path P is just the minimum of the two subpaths. So it's the minimum of lengths of the path from S to V and the path from V to S. From V to T. Okay? And then the previous discussion should make it clear why we define reach of V this way. It's a maximum over all shortest paths going through V of reach of V with respect to P. Okay? And so thinking back to this example, vertices on this island will have a small reach. Okay, so we have some measure of locality of the vertex. And we can use it to prune Dijkstra's algorithm. So suppose we are scanning vertex V.
Small or large?
Small.
Why? It should be large. They do not lie on the
Internal nodes.
Consider any intersection on the island.
Yeah.
Any shortest path going through that intersection will have one of the parts very small.
Yeah.
And that will
Ah, I see. I
Right,
see.
and
I see.
it's the minimum first.
I see.
Okay, it's the minimum and the maximum. So in other words, the vertex has a large reach if it's more or less in the middle of some long shortest path.
Mm-hmm.
Okay, and these vertices on the island are not in the middle of long.
And S are and T are not fixed in the definition.
No, there's no
Uh-huh.
SST,
I
S and
see.
T.
I
This
see.
is
I
reach
see.
of V with
Ah.
respect to the graph.
Uh-huh.
S and T cannot be fixed because we do preprocessing without knowing
I
what the
see.
T
I
is.
see.
Okay, so you're scanning vertex V and you sort of discovered a path to W of length d of W, and suppose you also have a lower bound on the distance from W to T. Okay, then if a reach of W is less than the minimum of this distance label of W and the lower bound on the distance from W to T, then you can prove W. Why? Because if this path were shortest path, then the reach of W will be greater or equal to this minimum. But it isn't, so it means that W is not on the shortest path, at least not on the shortest path which starts with this red path, which means that you don't need to look at it. And so you can prune it. So this is equivalent to, as a human, you don't search this island. Okay, and we can, if you think about it, to compute reaches, you sort of do all pair shortest path computation and a little bit more work, and it's not hard to see how you can compute reaches. But for the purpose of this talk, n squared is a very large number, so it's impractical to run an n squared algorithm, which is all pairs of shortest path algorithms on sparse graphs. So we need to do something faster, and it turns out that there are heuristics which compute good upper bounds on reaches faster. And its upper bounds are enough to prune, right? Because if reach is, if something is less than an upper bound on reach, then it's also less than reach. Okay, so we can efficiently compute upper bounds, but this is sort of still not practical. It's useful, but not practical for very large graphs. There is an additional idea we need, which is the idea of shortcuts. So, let's see. I guess I'm not talking about shortcuts, but so the idea of a shortcut is as follows. So, suppose you have a picture like this. Suppose this is of length 1,000, this is of length 1, this is 1,000. Okay, so reach. What is the reach of this vertex? It's clear that it's 1,001. So suppose I create a virtual highway of length 2 minus epsilon, so that I prefer it to. So this path is a little bit shorter than this path. What happens now? I claim reach of this vertex goes actually to 0. Right, because this is a shorter path, so all shortest paths at the end of this vertex, which involve this vertex, either end here or start here. Okay, so, and of course, if this was sort of a long path of ones, all vertices here will have their reach reduced, not to 0, but to something, sort of something 1,000 less, essentially. So you can introduce these virtual highways, and what they do is they reduce the reaches of vertices. Okay, and it turns out that this speeds up querying, and also it speeds up preprocessing. So
do you add those highways?
We add them to the graph, but we also add some information which tells them that this is a virtual arc and it corresponds to some path in the graph.
And why doesn't that prevent you from finding the exact path that doesn't?
Because
No,
it's the same
we are
length.
finding exact path.
The virtual length is the same as real one.
One epsilon.
Well, you can sort of prefer paths with fewer hops. You don't really need this epsilon.
So you use those virtual highways only for finding reaches, or?
No, for finding reaches, and also when we find the shortest path, we find it in the augmented graph, in the graph with these virtual highways added. But as I said, we also keep the historical information. We know that this virtual arc corresponds to this real path. So we can restore the path. So first we find an implicit representation of the path, and then we expand it to the real path. Okay, but let's go back and see. I didn't tell you how you find the lower bounds, right? So if you have landmarks, you can find lower bounds using landmarks. But in fact, for bidirectional algorithm, you don't need any additional information. You get lower bounds for free. Because suppose that the forward search should have searched this ball here, and the reverse search this ball here. And if this vertex hasn't been scanned by the reverse search, it means that this distance is less than the radius of the reverse search. So you can use that lower bound. So as the algorithm runs, you're getting better and better lower bounds for vertices you're considering now. So you'll search sort of dense space of vertices initially, but then you'll be searching sparser and sparser sets. So how do you compute reaches? So as I said, exact algorithm is essentially all pairs of shortest path algorithms with a little bit of bookkeeping added. This is, we have some improvements on that, but they're sort of constant factor improvements. And for just 300,000 vertices graph, which is small by what we want to do, it takes overnight. And it sort of goes quadratically, so to do the biggest graph we have, which is 30 million vertices, will take years. But we can compute upper bounds, at least heuristically, faster if you use shortcuts. And the idea is as follows. So instead of growing a shortest path tree from every vertex, we will grow a shortest path tree and stop when we are roughly 3 epsilon away. Okay? And we do it for every vertex. And this sort of limited balls allow us to bound reaches of most vertices whose reach is at most epsilon. That's the idea, sort of looking 3 epsilon away. You can almost, if there are no lone arcs sort of longer than epsilon, then it will be true that you will bound reaches of all vertices whose reach is at most epsilon. Here you may miss some, but it's okay, you're conservative, we're doing upper bound, so you bound reaches of not all but most vertices whose reach is epsilon. And then essentially you delete these vertices, your graph shrank, it's a smaller graph, you increase epsilon, and you repeat this. There are some technicalities. Actually, this is the ugliest part of the algorithm. The query algorithm is very simple. Here you have to worry about arcs which are longer than epsilon, and also you have to, since you deleted vertices with small reach, you are sort of forgetting about some short path segments, so you have to add some penalties to account for this. So there are some ugly parts to this algorithm, but it sort of works well because the graph shrinks at each iteration. And so that's what you get with the reach. Okay, so this is again the same thing as before, but as you notice now, there are lots of holes in the search space. And sort of the nice thing is that we have the data for road categories for the graph, but we're not using it. So this basically algorithm identified major roads. It's sort of went along major roads, and it didn't go to some local parts of the graph. And if these are not major roads in road classification, they should be in some sense. So this is actually better than road classification provided to you by Graph Vendor. Okay, and sort of in terms of experimental results, preprocessing is very expensive because this is reached still without using shortcuts. But storage overhead is smaller, and you get improvement in running time, although not for the graph of this size, not quite as good as that for out. So now, okay, so sorry, I had this slide. So now you can add shortcuts, and this is a picture I had on the blackboard over there. So you have shortcuts, and reaches of vertices are reduced, right? And you can do it sort of recursively, and the point is you can introduce very small number of shortcuts and reduce reaches of many vertices on certain classes of graphs. In particular for graphs of road networks, there is this natural highway hierarchy, and highways are very natural things to shortcut. The interesting thing is that the heuristic we use for shortcutting, which is actually due to Sanders and Schulze's, which we sort of adapted to reach computation, it doesn't know about highways, and it does something very simple-minded. What we do is, if we have so we have some constant cutoff, and if we see a vertex whose degree is less than this constant, we delete it from the graph and replace its arcs by a clique of arcs on its neighbors, so that if we sort of if this was our vertex and it had two neighbors, the vertex is deleted, but we add this arc of the length equal to the sum of those blocks. Okay, so it's a natural thing, and of course we are not losing any shortest path information, because we remember that that long arc corresponds to this two arc going through the vertex. And also, if you think about it, since the degree of shortcut vertex is bounded by a constant, the number of shortcut arcs we introduced is constant times the number of vertices. Okay, so we are guaranteed not to introduce too many shortcut arcs. And sort of the interesting thing is that, and we'll see this later, this very simple way of introducing shortcuts actually discovers some very interesting shortcuts along major highways. This is sort of probably because of the property of the road networks. Okay, and this greatly speeds up preprocessing because many vertices have small reach, so we can delete them. And also this greatly speeds up queries. In particular for big graphs, the implicit representation of shortest path has something like 50 arcs, even though the real path has something like 50,000 arcs. So we very quickly find the shortest path, and in fact the time to find the implicit representation of the shortest path is comparable to the time it takes to traverse the real path in the graph. And of course shortcuts require some extra space, but we have a bound on that. And so this is the picture of shortest path with reaches. As you can see, this picture is not connected. And this is because we draw all the vertices visited. And because of shortcut arcs, you can jump over a big area. So this picture is much sparsified compared to the previous one. Okay, and in terms of numbers, first of all, preprocessing gets much faster. We get only 17 minutes because of shortcuts. We have to pay in storage for shortcuts, but the number of operations and the running time goes down a lot. Okay, so the shortcuts really pay for themselves. Okay, and now we have this reaches and we have alt algorithm. And these are sort of orthogonal ideas, and they can be combined together. So if you think about it, reaches sparsify, prune your search, and A-star search directs the search. So if you look at this picture, this sort of search was sort of aimlessly going back and forward and so on. And intuitively, you shouldn't be going here, for example, here. You should be directed, and that's the reason for using alt here. So alt can be combined with reach pruning, but you have to be careful. Implicit lower bounds no longer work, because you are doing distances, and the reaches are in the original space, and your Dijkstra computation runs in the transformed space. So balls in the transformed space look very different from balls in the original space.